All right, let's finish this up again. We should be in good shape. So behind me, I just put on there for the test for Wednesday. Blue sheet's kind of the key to everything, right? So blue sheet, periodic table, note sheet. I don't know, just to have a little bit less sheets all over the place. So you're going to want to copy this onto your note sheet that's on the green sheet. I don't know, just one less sheet that be laying around, right? So this is for sure going to want to go on your note sheet. So, and no scratch paper. Okay, so for the test, blue sheet's the key. You can use the blue sheet, note sheet, periodic table. That should do it. That should be good. Okay, let's finish this up. Let's look at this quiz again. Our goal today, we'll just finish everything up. We're going to do the last two quiz questions in class. So that should do us. Number 6, we've looked at this previously. The next one is 19. All right, so 19, the question is, look at the electronegativity of hydrogen. All right, well, let's do that. What is the electronegativity of hydrogen? So the electronegativity of hydrogen is, if it doesn't glare, there's 2.20, 2.20. Okay, so I looked at the electronegativity of hydrogen and I wrote down that it's 2.20. Which of the following is hydrogen most likely to combine to form hydride? Hydride is H-1. So that means it has to be this XH. Hydrogen is going to be -1, which means hydrogen has to have the higher electronegativity, right? Whichever one has the highest electronegativity gets assigned the negative charge. So hydrogen is 2.20. So this X, which I'm saying is going to be one of these X just has to be less than 2.20. We're just looking for one that's less than 2.20. So that's going to get assigned the positive charge and hydrogen is going to get assigned the negative charge. 21. What's next? 21. Okay, 21. I highlighted these because it was on the board. So they're actually on here. And I was able to find them without calculating everything, and I color coded them. So based on the bond type triangle, which of these covalent compounds have the greatest ionic character? Well, whichever one is closest to the ionic line, hopefully towards the top even. And the best we can do, and I didn't mean to circle this, I ran out of colors when I got to here and I grabbed my red pen and it happens to be that, but this one's closest to the ionic. And again, I was just able to find them. I didn't mean to circle it in red. I just didn't have a big color. So whichever one's closest to the ionic line here, which of course is this baby, right? 21, 22, 23. Based on the given bond type triangle, what is the highest possible average electronegativity a compound can have to still retain some metallic character? So we're talking about a metal. And the average electronegativity is on the x-axis. Highest average to still be have metallic character. Here's my metal. And the highest I can get would be in this corner right here, right? The highest average would be in this corner. And you got to go down to get your average that's in this corner, the highest average that's in this corner. And the highest average that's in this corner that fits that question. It looks to be, if I go down about right in there, huh? Looks to be the highest average. That'll keep that 23. So that was 23, 20. We got here, 25. Okay, it's 25. What is hybridization of the central atom? I thought we drew this out somewhere, but let's do this. So the valence electrons is going to be 3 times 7. And this is going to be +1 due to the negative ion charge. Iodine's in group 17. So we're going to end up with 22 valence electrons. So I think this is the one where I did draw this out because I added an extra iodine. Somewhere we drew this out in a previous question, maybe, I don't know. So we've got 3 iodine, we're going to connect them. So we connected them with a bond. Now we're going to fill the outside terminal octets. And that gets me 16, right? 16 out of the 22 I need to add. I can't do double bonds. I'm just going to add the remaining 6 electrons to the central atom. And this is more than likely, if you see it somewhere, since it's an ion, it will have a bracket around it and a negative charge. So you can look up hybridization on the blue sheet for 2 bonding domains and 3 non-bonding domains, right? That's a 2-3. Okay, 27 is a good question. 27 and 28 we have to do. 27 and 28. So 27, which of the following compounds would be non-polar? Okay, so remember, to be non-polar, we need equal angles, and we have that because everything here is going to be a 4-0. Everything here is going to be a 4-0, but for this to be non-polar, the outside terminal atoms have to pull with equal strength, which means they have to match. Now, if you look at, for this one right here, I'm just going to grab this. Speed. So if I pretended this was a BR, I mean, that's not going to work, right? Because these 3 are going to pull differently on the electrons than this single one. There's no way this can all cancel out. And the other problem is this. You might look at, if you drew B out on paper, I'm going to point this out. You could have a CL like this and a CL like this. And on paper, you could put a BR crossed and a BR crossed and say, well, Keith, that cancels out. I got one pulling left, the same as the one pulling right, and the one up is pulling with down. Hey, that cancels out. We're having a party, right? And the answer to that is no, 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 because you're looking at a 2-dimensional picture when it's really this 3D this 3D structure. There is no way I can put 2 reds straight across from each other. There's just no way. So if I stick another red, it doesn't matter where I stick it, you're going to get the same compound. So if I put these reds here, right, there's no way this can cancel out. There's just no way. The only way for this to cancel is for this one. The outside terminal atoms have to be exactly the same, so the pull is exactly the same. And then it will have the key, and this is going to be the lab. It's going to have no net dipole or no dipole moment. Okay, 28, what's the molecular formula? What are we looking at here? 28. How many carbons do I have? 1, 2, 3, 4 carbons, right? 4 carbons. How many hydrogens? 3, 4, 5, 6, 7, 8. Looks like 8. How many oxygens? Like 2, huh? That's something that looks like that. Yeah. Okay. Let's finish up hybridization. So we're going to finish up hybridization and talk about sigma and pi bonds, and that is pretty much going to do it. So we're really on page 15 is where the recordings are that I'm going to use. But then this, all of this here is talking about hybridization that I have highlighted in yellow. And we'll do the last 2 quiz questions. So I am going to stop sharing, switch screens, which I messed up on the other day. So let's see, I've got to share screen. Oop. Should be right here. Okay. Let's see what this volume does here. Okay, I'm going to fast forward. Now, we did this last time, but maybe you had some sleepy eyes. I don't know. I'm going to go towards the end of this one.
That's both carbons are sp3 hybrids. Something happens through the 2 groups. The structure will only go to the sp3.
Now, this for lab, again, we're going to be looking for lab, depending upon your lab instructor, if they want this 3D drawing with the wedge and dashes. Here's the wedge would be coming towards you and the dashes would be behind.
Start in black where they shown. It's a solid line.
Now, both of these carbons are sp3 hybridized. Now, how do you get sp3 hybridized? Remember, carbon is 1s2. We don't care about those 1s2s. 1s2, 2s2, 2p2. Again, the 4 valence electrons are 2s2, 2p2. One goes out of the s and goes into the p. And then all of those morph into hybrid orbitals. You do not have an S anymore. You do not have a P anymore. You have sp3 hybrid orbitals. Both carbons are sp3 hybridized on this.
And each carbon has 4 single bonds. Thus, both carbons are sp3 hybridized. Starting the 2 sp3 hybridized by forming the CT sigma bond.
Sigma bond right there, carbon to carbon sigma bond.
And 6 hydrogen sigma bonds formed, which forms the final 3 initial structure for that. The 2 additional applies to all 4 bond angles to 90 degrees. However, in employing the basic principles of hybridization theory, see that the bond angles fall nearly 29.5 degrees. Now that the molecular geometry for ethane dimensions have been determined, we can begin to examine some of ethane's. Similar to the first step of Sp3 hybridization, one can imagine promoting that two S atomic orbital, non-occupied two atomic orbital. Next to the 2s atomic orbital with 2 of the 2p atomic orbitals creates 3 new degenerate energy hybrid orbitals.
Let's stop right there. Sp2 hybrid orbitals. How many equivalent orbitals are there? 3, right? And you could add up, you'd have an S1 for a superscript, right? Otherwise it wouldn't be there. You have 3 hybrid orbitals, but look at this. You have a regular P-shaped orbital left over. Again, this is not an S shape. This is not a P shape. It's a hybrid in between. For Sp2 hybridization, you have 3 hybrid orbitals, a regular P left over.
All orbitals think that these orbitals has 3-dimensional shapes.
Looks like a nookie pacifier. Yes, looks like a nook.
Three electrons. One electron.
Regular P, non-hybridized.
We superimpose all 3 Sp2 hydrogens. Hybridized 2 receiver by the atom. We shall have electrons. Shrunk to each other's. That's the the structure will probably is consumed by the best and why it is shown. Again, remember this reminds you no law is it's important to remember that each of the 2 Sp2 hybrid orbitals is one electron capable of forming a sigma bond. Thus, the Sp2 hybridized carbon is not capable of forming 3 sigma bonds.
1 pi bond.
Two-dimensional Lewis C is 3 sigma bonds and 1 pi bond. Thus, both carbons are Sp2. Forming the CC sigma bond. Next, hydrogen sigma bond, which forms the planar sigma bond framework.
All sigma so far, right? So far, each carbon has 3 sigma bonds. Each carbon has 3 sigma bonds.
To form the second bond between the carbons called the pi bond, we can imagine that the 2 of these parallel unhybridized 2p atomic orbitals overlap. Then the overlap 2 electrons be shared by each carbon valence.
This is your double bond. This is your pi bond. Notice it said parallel P's. Both of these would be what we would say it was in our y-axis, correct? Both of those were straight up and down, so they're parallel to each other. So how do you get a pi bond? Overlapping parallel regular P unhybridized orbitals. Okay, pi bond. Overlapping parallel P's unhybridized orbitals.
hydridization scale. In a better understanding of the pipeline, we should recall the natural shape of the unhybridized converters. Draw the molecule this way. Thus, you will often see the pipeline represented in this green form on the right.
All right, SP hybridization. How many equivalent orbitals are you going to have that are exactly the same? 2, right? 1 S and 1 P.
Similar to the first set of Sp3 and Sp2 hybridization, one can imagine counting at 1 P, 2 S the 2s atomic orbital with one of the 2p atomic orbitals called the 2u generate energy.
So now you have 2 hybrid orbitals and 2 regular p orbitals left over, right? 2 regular p's left over.
The shape of the new sp hybrid orbital is then characterized as 1 part s and 1 part p. As with all orbitals, look at these hybrid orbitals, three-dimensional shapes, where we find them from 90% of the time. The sp hybrid are in one set. All the sp hybrid orbitals are Sp23. That's the essentially show. Is shown to the third bit of this. Like on the portions. Thus, they are oriented 180 degrees apart. It's important to understand the structure will often draw the sp hybrid started on the one shown. Solid lines are in plain order, shaded lobes are in marginal order, and then logical. The two sp hybrid orbitals use one electron, capable of running. The sp hybrid will start in the same 2 sigma bonds. The seven. Two-dimensional Lewis diagram, we see that each carbon forms 2 sigma bonds and 2 pi bonds. Thus, both carbons are sp hybrids. Starting with the 2 sp hybridized bonds, and we can construct the molecule in 3 dimensions by forming the sigma bond.
Sigma bond.
2 carbon hydrogen sigma bond formed, which affords a linear sigma bond merged electron. To form the second and third bonds, which we call the pi bonds, we can imagine
So those are parallel. The red would be what we would probably say is in the y-axis and the blue is in the x-axis. They have to be parallel with each other. This is 2 pi bonds. So if you have a triple bond, you have a sigma here in the middle and 2 pi bonds. How do you get pi bonds again? Overlapping parallel p orbitals. Now this is the hybridization that only goes to sp, but we can mix in the D's as well. So if you can have sp3 D hybridization, sp3d2 hybridization, and so on. You wouldn't have any sp or D's, they would be morphed together, called hybrids.
To better understand bonds, we should recall the actual shape of the unhybridized superorbitals. Which allows the share of these 4 electrons. Instead of getting what we call the molecule this way, as you will often see that ions represent.
That's the only one I ever reply on. I never touch any of it other than that one. Here's the one I want to show you real quick.
Both. No single.
It's carbon dioxide.
For both ions to form, rotate the oxygen on the right form.
Notice that the oxygen is sp2 hybridized. The oxygen has a regular P left over, correct? What is the carbon hybridized? Sp, right? Sp. Carbon is going to form a double bond on each side for carbon dioxide. So carbon is going to form 2 pi bonds. The oxygens are going to form 1 pi bond. How do you get a pi bond? Parallel P's overlap. Notice that they've rotated this oxygen.
That's both ions. Perpendicular to each other. Indicating a lot of layers on each point of the map are perpendicular to each other.
All right, let's go to our quiz. Then we're going to go back to our learning guide. Let's do the last question on the quiz. First of all, what is the hybridization of this carbon? What is the hybridization of this carbon? I'm going to go back to my same. This carbon right here, the hybridization, well, I guess we should identify the bonds. This is sigma, right? This has to be sigma, sigma. If you have a double bond, one of them is sigma and one of them is pi, correct? If you have a double bond, one of them's got to be a pi bond. So the hybridization of this carbon here is sp2. This gets you the 3 sigma bonds, correct? sp2 is the 3 sigmas. You have a regular P left over for the pi bond. This is a sigma bond. This is a sigma bond. So on the test, I think I numbered these carbons. 1, 2, 3, 4. I think they have numbers. if I remember right, but there's a similar diagram on the test. This carbon right here, carbon 2, has 3 sigmas and a pi bond, right? So this carbon is sp2 hybridized. This carbon right here, carbon 3, has a triple bond with carbon 4. How do you get a triple bond? 2 pi's and a sigma, correct? 2 pi's and a sigma. What is the hybridization for carbon 3 and carbon 4? Carbon 3 and carbon 4, sp hybridized. How do you know it's sp3 hybridized? You have to have each of those has to have 2 regular P's left over, right? 2 regular P's left over that are parallel. So each of these does, this carbon here does 2 sigmas and 2 pi's. Carbon 3 and 4. So what do we got? We have 3 pi bonds here, huh? There's only one choice that has 3 pi bonds, huh? No, there's 2 choices, 3 pi bonds. What do we got? 7 sigmas and 3 pi's? I think we got 7 sigmas and 3 pi's. Let's go up to 29. 29, which of the following statements is correct? The overlap between an s and a p orbital is called a pi bond. How do you get a pi bond? Overlapping parallel p's, correct? Overlapping parallel p's. That's just garbage. The overlap of 2 s orbitals in H2 is called a sigma bond. That is correct. That's the only thing hydrogen can do. Hydrogen is just an S, right? Each hydrogen is 1s1 with another hydrogen that's 1s1. They'll share an electron from each. HF is formed from the overlap HF is formed from the overlap of a hydrogen 1s orbital, that would work, with a fluorine 2s. What's the electron configuration notation of fluorine? 1s2, 2s2, 2p5. So what's going to happen is it's going to be a 2p orbital. This should be a 2p orbital here. There's where you only have 1 electron, right? There's 1 electron in a p is going to overlap from this 1s electron here. This should be a 2p. Okay, that should complete this quiz. Let's go back into the learning guide and finish this, talking about this. There's an example from Owl in here as well. Again, this is the regular electron configuration notation for carbon. If we make a hybrid, sp3 hybrids, one of these goes out of the 2s and goes into the 2p, correct? So we'd have 1, 1, 1, 1. Okay. And again, you do not have, this is what it looks like. You don't have really S-shaped anymore. You don't have P-shaped anymore. You have these in-between hybrids. And what shape do you get when it does this? Tetrahedral, correct? Sp3 is tetrahedral. You have 4 equivalent orbitals. These hybrids get as far apart from each other as possible, 109.5 degrees. Then for tetrahedral, if you have a non-bonded pair, then we have a 3-1 configuration. It goes from 109.5 to 107.5. Then if we have a 2-2 configuration, the angle goes down to 104.5, which is water. If you have sp2 hybridization, that's where we can get this double bond because we have a regular p orbital left over, right? Regular p left over to get our pi bond. And here is what that actually would look like. Here's our carbon to carbon pi bond, regular p left over. If we have sp hybridization, we have 2 p's left over. 2 p's, then we can get a triple bond in the middle, right? We get our triple bond. If you put this all together, it kind of looks like this, but the video showed it pretty well. One was in red and one was in blue, right? What type of shapes do we get? Sp3 hybridization is always tetrahedral. Sp2 trigonoplanar, and Sp ends up being linear. Well, we can also have Sp3D hybridization, or it promotes an electron into the D. So right now, this is 3s2, 3p3. One of them goes out of the S into the D. We can combine all of these, and we're going to end up with 5 equivalent orbitals, correct? 1s, 1d, and 3p get together. We also can have sp3d2 hybridization. And here's the shapes we get for those hybridizations. Here's sp3d2 hybridization. This would be 6, right? 6 equivalent orbitals total. Let's do this. Carbon 1, 2, 3. This is maybe, I've got carbon 1 identified. Let's see what it says. The orbital hybridization scheme used by the carbon atom. Carbon 1 is. Do you see any double bonds for that carbon? No double bonds, correct? So this should be sp3, right? sp3. This molecule has 13 sigma and 1 pi. Well, how many pi bonds do you have? Right here, correct? If you have a double bond, it's a pi bond. So this one is a pi. The rest of these are sigmas. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, I think. Did I lose track? 13 sigmas in a pi? Is that right? I think it's 13 sigmas in a pi. Okay. Here's some valence bond terminology. Overlap, 2 orbitals existing in the same region of space. You could have a lone pair, bonding pair, central atom, hybridization, hybrid orbitals. Sigma bond, pi bond, single bond, double bond. Hopefully triple's on the next page because a triple is going to be a sigma and 2 pi's, right? Triple is going to be a sigma and 2 pi's. Here are some OWL questions. Yes, I do have triple bond at the top of page 22. Triple bond, 1 sigma and 2 pi's. All right, here's some pi, or here's some pi questions. Here's some OWL questions. All right, so what do we got here? PCl3, and we can look at it. How many atoms are bonded to the central atom? 3, of course. If you consider only the 3 outer atoms, what shape do they define? A triangle. Consider the bond angles on the central atom. Do they all have approximately the same numerical value? Yes, and you could draw this thing out, right? Maybe we should do that quick. Phosphorus, how many valence electrons for phosphorus? 5. And then we would have plus 3 times 7. We would get 26. But I'm hoping you know what this looks like here. I'm hoping on the test, it takes you about just as much time as I just did to draw this thing out, right? I'm hoping. We've got 1 non-bonding pair. This is a 3-1, right? This is a 3-1, which hopefully you predicted. There's nothing up here. You got to have a non-bonded pair up there. All right, consider the bond angles on the central atom. Do they have approximate? Yes. What is the approximate bond angle? 109. Okay, it says the word approximate, right? If we actually did a 3-1 on our blue sheet, 107.5. But again, the word approximate, 109, that's fine. Does the central atom lie in the same plane defined by the 3 other atoms? No, right? You can't draw a line and connect all 4 atoms, correct? That would mean the same plane. You cannot draw a line and connect them all. Are all 3 positions about the central atom equivalent, or are they different? They're the same. They're all pointing down at 107.5. And the molecular geometry, trigonopyramidal. And the next one should be similar. We've got ICl5. And you could rotate this. And if we would have 6 times 7, we have 42 valence electrons, right? 42. Both of these are in group 17. Both are in group 17. And if we drew this out, And then did our terminal atoms. Oops, oh, all right. That's 40 out of my 42, right? 40 out of my 42. So I'd have one non-bonded pair somewhere that I'm gonna put in red. That's what that looks like. And then all of this should follow through. That gets us perfectly to Lewis structures to the end. Any final questions? The description of the test is online in Canvas, right? I think it's 30 questions. Right, 30 questions. So we ended perfectly lined up. That's the end. We did well. The owl and the quiz are tonight at midnight, right? The owl and the quiz tonight at midnight.